Today, Seattle 4 can showcase a Seattle-based, space-oriented scientist, not spacey, space-oriented, a physical oceanographer with degrees from Florida Institute of Technology, the University of Connecticut, and our own University of Washington, a senior scientist with NOAA and NASA on ocean sensing from space. He co-founded Seattle nonprofit Earth and Space Research. Its mission is to increase societal understanding of the Earth system through scientific research and public education. In 2009, he'll oversee the NASA Argentina launch of Aquarius mission to study the interactions between ocean circulation, global water cycle, and climate, all by measuring the ocean's salinity from space. Don't we wonder about the global interaction of ocean, earth, and climate? To show us what's being learned and what can be learned, please welcome Dr. Gary Lagerloef.
All right, it worked the first time. That's good. Okay, thank you, John, for that really glowing introduction. And I also want to thank all of the Rotary Club for this invitation to come and speak with you today. Especially, I want to thank my friend Geraldine Brousseau, one of your members who orchestrated this this lecture. It's really an honor to be invited to come here. I also want to acknowledge this table here in the front, a number of my colleagues from Earth and Space Research, my co-conspirators in this scientific endeavor that we'll talk a little bit about today. And also I want to add my own notes of congratulations to the academic achievers who are being honored here today, and in hopes that what I'll talk about today about climate change in the space age might inspire some of you towards a career in science or engineering or something to do with studying the environment or climate change. So that's the subject of my talk today, is actually climate in the space age. And this is going to be a bit of a science lecture. So I'm going to ask you to set aside your apprehensions about being back in Physics 101 and so forth and so on. I'll try and make this stuff as simple as possible. But I do want to talk a little bit about climate change. And I want to talk about what the space program is doing in terms of studying what's happening in the climate. And I'll give you some examples of that. But let's start here. Uh-oh. There, whoops, back up. Okay, there we go. This globe here is a picture I'm sure is familiar to many of you. It's the first full disk image of the Earth taken from space by astronauts. This was the Apollo 17 mission, the last Apollo mission that ever went to the moon in December 1972. It's the first time we've been able to see the whole globe as one disk. Most of the other pictures that had been taken from space at that time either showed part of the Earth or half of it was in shadow and so forth. This was the first one that showed it what has now become sort of the image of the blue marble. But one of the advantages, what this picture illustrates is a specific advantage that we have by looking at the Earth from space, is that we can see the big picture. We can see a lot of things going on at once. And I hope to be able to illustrate some of those things today. Now, when we think about the space program in this country, of course, many of us remember the Apollo program back in the 1960s and early 70s. I certainly grew up sitting in front of my television set the whole time there was any space mission going on. That doesn't happen quite so much anymore, but when we hear about things in the news, it's usually a shuttle launch happening, which there is one scheduled for this coming weekend, or maybe you hear something about a probe landing on Mars, which happened this past weekend. The Phoenix probe was safely landed on Mars to begin studies of the north polar regions of the planet there. But what's happening in Earth science? You don't hear too much about that in news, but there's actually a lot going on in Earth science. This is a portfolio, is about the best way to describe it, of all of the different missions that NASA has a participation in. Either NASA's built the whole mission or they participated with other partners, either from other agencies in the U.S. government or other international space organizations from other countries. that are making various kinds of observations of the Earth. There are about 19 or 20 satellites in this picture, just to give you an idea that there's an awful lot going on right now in the way of Earth science. I've circled a couple of these, the Jason satellite, the QuickSat satellite, the Topex satellite, Grace, and Aqua. I'm going to show you some measurements from those satellites. There's not enough time in the whole afternoon to go through all of the information that's provided by all of these satellites, but I'm going to give you a sampling here. Just to give you an idea of what some of the things are being measured here, this is just a bit of a laundry list. In the atmosphere, we're measuring things like temperature, tropical storms, ozone, the ozone hole, for example, changes in the humidity of the atmosphere. We can measure rainfall. We can look at cloud structure using profiling radars. We can determine evaporation off the sea surface. We can look at aerosols, carbon dioxide, carbon monoxide. We can look at the energy balance of the Earth. There's lots of things going on. Those items that I've highlighted there in a red color are some things I'm going to talk a little bit about during this discussion. On the ocean side, we can measure sea level, surface winds, currents, surface temperatures, ocean salinity coming soon, not quite there yet. And in the cryosphere, that's the ice part of our planet, sea ice cover and ice sheet mass and ice sheet elevation are being measured. And this is not a complete list. I've left out a lot of things, particularly all the land processes that are being studied by satellite, because I don't want to spend the whole day rattling off all of this stuff. Now, I'm going to introduce you to a couple of what I would call old friends in terms of the satellites. These are programs that I've worked on for about 20 years. One of them is a program to map sea level with satellites. Now, don't forget, I'm an oceanographer, so I'm highlighting more of the ocean-related satellites in this discussion today. This satellite here is called Jason 1. It's been orbiting for about 5 or 6 years now. It's actually the successor to another satellite called Topex, which was launched back in 1993. And these two satellites together form now a 15-year-long time series of information about changes in sea level. The most important thing that I want to point out here is a little bit about the technology of this. This satellite uses a radar system, kind of like the same radar system that a policeman might use to see if you're going too fast down the road. This radar system is very precise, and from an altitude of about 800 miles, which is 1,300 kilometers above the Earth, it actually sends a radar beam down and waits for the signal to bounce back up off the surface, and by measuring the time delay, it can calculate we can calculate the height of the satellite above the sea surface to a precision of about 2 centimeters, that's less than an inch, and use that to map the topography, the shape of the ocean surface. And we can also watch how it varies. So this map that you see down here is a map that was created just a week ago from data from this satellite that shows the differences of sea level from where it would normally be. So the colors that you see here that are blue are areas of lower than average sea level, and areas that are colored red are higher than average sea level, and the rest of the stuff that's sort of yellow and green is more or less about average. We use this information for a number of things, but what I'm going to talk about here is we use it to determine ocean currents, because it's the slope of sea level that helps propel ocean currents. And the other instrument that I've been working on for a long time is one that measures ocean winds from space. This is a different type of radar. It's called a scatterometer, and it measures ocean winds by sending another radar beam, but this time instead of straight down, it sends it off at an angle. And it looks at how strong the echo is coming back. If the sea is very flat, that echo will bounce off in the opposite direction and you won't receive much of a signal on return. But if the sea is really rough, if the wind is blowing really strong, then you get a strong echo coming back, and that gives you an indication of the intensity of the wind. Now, on the bottom of the satellite here, you see this little antenna. That actually spins around like this. So as the satellite goes along, it makes a conical scan of the surface, and by looking at the same spot on the sea surface from a couple of different directions, we can actually resolve the direction of the wind as well as the speed of the wind, and you can see a map of the kind of information we can get out of this satellite. This is a map of a tropical storm back in 2006. So we put these two pieces of information together in my group here at Earth and Space Research, and we've developed a product that determines the ocean circulation from these two satellite measurements. We call this project OSCAR. It stands for Ocean Surface Currents Analysis Real Time. We do this in cooperation with NOAA, the National Oceanic and Atmospheric Administration. We have a website. You can go to this website here and find out anything you want to know about the ocean currents for the last 15 years, including what they were about a week ago. One of the most important pieces of research that we do with this data product that has to do with climate and climate change is that we studied El Nino with this. Actually, this is one of the most important motivations for doing this research in the first place. We wanted to understand the interaction between the circulation and what happens in the tropics during El Nino. So let me take a second to describe a little bit about what El Nino is. This picture up here on the top is a map of our surface currents. All those little arrows, those little feather arrows that you see there are vectors that point the direction and the speed of the current. And then the colors that you see are sea surface temperatures derived from satellite sensors. And you can see that in the typical situation in the equatorial Pacific, here's South America over here, here's Australia and Indonesia, the currents generally flow from east to west along the equator. And they drag this cold water from the coast of South America up onto the equator and pull it towards the west. So we have this cool temperature region along the equator in the equatorial Pacific. All the warm water collects over here in the west. Now, when we have an El Nino, what happens is that the currents turn and go the other direction. And they bring all of that warm water back across the Pacific Ocean. And as you can see, in 1997, we had the largest El Nino that was recorded in the past 100 years. And this is what was going on from our satellite observations during that time. All this warm water flooded across the equatorial Pacific Ocean. And whereas most of the warmth was over here, and that's where most of the energy goes into the atmosphere, when El Nino happens, that warm water moves to the east and moves the place where the energy goes into the atmosphere. That changes the atmospheric circulation. It modifies the jet stream. It changes the weather patterns along the west coast of North America. That's why we have intense rainfall in California, let's say, during an El Nino year and so forth. And it even has impacts all the way over to the east coast. So it's an important weather phenomenon, and the work that we're doing with these surface currents is really helping us understand that a lot better. Now, what's going on in terms of recent conditions? In the equatorial Pacific, as of last fall, we were in a condition known as La Nina. La Nina is the little sister of El Nino. And La Nina happens when the trade winds, which blow from east to west, strengthen those currents and bring more cold water up into the equatorial region. And that actually creates colder than normal conditions along the equator, and that changes the weather patterns in a different way. The La Nina conditions tend to bring a wetter winter to the Pacific Northwest, and I think we experienced some of that weather in early December when we had some pretty severe flooding and rainfall here. What's happening today? This is our map from last week. All right, this is what's going on right now. What we've seen here is that the surface currents have reversed and are now flowing towards the east again. But the official forecast that we get from NOAA indicates that La Nina conditions are forecast to persist for the next few months. But our data indicate that we might be heading into an El Nino. So you heard it here first, okay? We're predicting an El Nino for later this year. Let's see what happens. Okay, now I'm going to shift gears and get away from El Nino, which is a climate variability that happens on a period of about 4 or 5 years or so, and talk about longer-term climate change. This is a diagram of the temperature, the average temperature of the surface of the Earth over the last 150 years. If you've been following any of the news stories about global warming, you may have seen a picture like this. This comes from the Intergovernmental Panel on Climate Change report that was published last year. A couple of things to note about this picture is, let me move the next piece down. Over the last 150 years, this red line gives you the average temperature increase that's occurred over 150 years. But if you look back just 100 years, that's the blue line here. You see that the slope is steeper. And then if you look back just 50 years, it's steeper still. And then if you look at just the last 25 years, you see it's even steeper still. So the warming of the planet that we're measuring from surface-based temperature measurements around the world, including the ocean, indicate that there's an increase in the rate of climate change, of global warming. The rise in the last 25 years equals as much temperature change as we saw in the 100 years previous to that. So things are starting to happen more quickly. What I'm showing here is what point in time that picture that I showed you at the beginning from Apollo 17 took place. So just in this period, since the 1970s, we've seen the most rapid increase in global warming, and it's also the same period of time that we've developed most of the Earth remote sensing satellites that we can use to study the processes that are going on in the Earth while this global warming is taking place. So that's what this picture says. Now, this diagram here talks about changes in temperature in the atmosphere that's based on satellite data. And there's a bit of a story behind this one. This uses a satellite instrument that comes on weather satellites that probes the atmosphere and uses microwave emissions from the atmosphere to tell both the temperature and the humidity of the lower part of the atmosphere. Now, in 1990, some researchers from the University of Alabama at Huntsville, that's what that UAH says, published an article that said that they took this data and they measured a downward trend. In other words, the atmosphere looked like it was cooling off at the same time that the surface temperatures were warming up. And they said, what gives? Something's wrong here. A bunch of global warming skeptics jumped on that and said, well, obviously global warming is not for real because these guys don't know what's going on, and so forth and so on. A few years later, a group in California, Remote Sensing Systems, figured out that there was a calibration error in those satellite data, and they made some corrections, and they figured out that if you take into correct for these calibration errors, you get an increasing trend, so that the atmospheric trends do actually, in fact, agree with what we're observing on the ground. Well, the University of Alabama Huntsville guys weren't to be outdone. They went back and redid their calculations, and they said, no, it's really cooling off. And it actually took about another 6 or 7 years before they all got it sorted out, but they did finally all agree on the correct calibration, and they also were comparing their results with weather balloon data, and that in turn revealed some discrepancies with the weather balloon data, which were then corrected, and now everything agrees. They all got it figured out, and the trend is actually about the same as it is at the surface, about 0.18 degrees Celsius per decade, which is about the same that we've seen in the last 20 years from the surface observations, which is about, pretty close to 2 degrees per century. That's the rate of atmospheric warming that we're seeing right now. So we have actually validated what the greenhouse effect of how the atmosphere is warming up due to the radiation balance has actually been validated by these data with a lot of work, and it's a good lesson in how the scientific process takes place. We all check each other's work. If we come up with a finding that's surprising, everybody goes and looks at it and makes sure that we've done it right, and it usually takes a few iterations and sometimes some controversy, and then we get the answer right. The first weather satellite image of the Earth was taken back in 1960. I found this on a NASA archive the other day, and I thought it would be interesting to show that. But I want to move on to the next picture, because one of the most important applications of satellite data, of course, is weather forecasting, and particularly severe weather events. This is an image of Hurricane Katrina, and we all remember that event. And this is when it was reaching Category 5, just as it was on its way to New Orleans, and created a great deal of devastation in New Orleans and along the Gulf Coast. And this created quite a bit of speculation about the relationship between tropical storms and hurricanes and global warming. It turns out also in 2005, a study was published that used satellite data for the last 30 years, the same kind of imagery data that I just showed you there, and categorized the intensity of storms. And they just basically did a census, global census, and they averaged the data over 5-year intervals. And what they found out was that storms that achieve Category 1, which is the lowest threshold of becoming hurricane status, those storms declined over time. The next categories 2 and 3 were about the same, but the storms that achieved categories 4 and 5 showed an increase in trend over time. So there seems to be some connection between hurricane intensity and changes in the climate. The other most important thing that we can observe from satellite that's an indicator of climate change is global sea level. That altimeter satellite that I described to you earlier that we use to map out ocean currents is also used to map global average sea level rise, because we're mapping sea level over the entire planet. Now, what you're seeing here is the last 15 years of data since we started taking these observations, and as you can see, sea level is climbing very steadily during that whole time. The data have these wiggles in it because those are the seasonal cycles. As the northern hemisphere warms up, the water expands because the ocean gets warmer, and in the wintertime it contracts, so the sea level goes up and down with the seasons, but there's also a clear trend that's going on there as well. Now, where's that sea level rise coming from? First of all, the rate is about 33 centimeters. That's about 1 foot in a century. So if sea level continues to change at the current rate, by the end of the century it'll be about 1 foot higher than it is today. But that rate is actually about twice what we observed during the last century. And what we really don't know yet, we don't have long enough observations to tell, is whether this is accelerating or has it just reached a new sort of steady state rate of increase. The other thing is that about half of the sea level rise is, about half the sea level rise is due to thermal expansion of the water as the ocean warms, and the other half is due to water that's coming in from someplace else, and that someplace else is the land. It's coming from melting ice sheets, and it's coming from alpine glaciers. Now, the next satellite I want to introduce you to is one called GRACE. GRACE stands for the Gravity Recovery and Climate Experiment. It's a satellite that actually measures slight, subtle changes in the gravitational field of the Earth's surface. Now, this is another example of really amazing technology to me. It consists of two satellites flying in tandem, one behind the other, in the same orbit. They're actually separated by about 200 kilometers, and they send a microwave signal back and forth to each other, and they watch how their distance increases and decreases over time as they go on orbit. And so that actually reflects the variations in the gravitation or the mass of the structures at the surface of the Earth. So if the first satellite comes over a mountain range, that extra bit of gravity pulls it ahead a little bit, so its separation distance increases. And as it goes past the mountain, the other one will catch up. And by correcting for all these measurements, you can actually map out the gravitational acceleration of the surface of the Earth, and you can see its changes. You can actually see the variations of the gravitational pull at the surface of the Earth due to the changes in the amount of water that's stored at the surface. If you took a body of water 1 centimeter thick and covered the state of Washington with it, then you let it all evaporate, this satellite would be able to tell you how much, that it would be able to detect that change of 1 centimeter of water. That's how precise this instrument is. Well, what are we doing with this data? Well, one of the things we're doing is looking at the massive ice sheets, because you really can't do that any other way. You can't go out there traipsing around on glaciers and really get the kind of accurate measurements you need to understand the whole mass balance of the ice sheets. But this gravity measuring mission can do that. It can actually detect the change of the mass of the ice sheets in terms of the equivalent amount of water that's either coming into the ice sheet or going out. And so this is what this diagram here is showing, and this data starts in about 2002, and this is a map of how this data is focused over Greenland here. This is actually Greenland, and it shows that Greenland is losing mass at a rate of about 231 cubic kilometers per year. And that's about enough water to raise sea level by 0.5 millimeter every year. And the same thing's going on in Antarctica as well. You can do the same kind of processing with this data and come up with a mass change of the Antarctic continent. What we know in Antarctica is that most of the ice is being lost here in what's called the West Antarctic ice shelf. Then the rate there in Antarctica, even though it's bigger, the rate is about the same as it is of Greenland, and it's again about 0.4 millimeters a year. So if we add these two together, both Greenland and Antarctica, the GRACE data show that about a third of the sea level rise that we're seeing with the altimeter data is actually coming from these ice sheets. Now, the other thing that's really happened, this is the big climate story of 2007, and I think many climatologists are really eagerly awaiting to see what's going to happen this year. The Arctic sea ice cover is starting to shrink rapidly. This is a diagram that shows how much ice cover there is over the Arctic, how much ice cover there was over the Arctic in 2005 at the end of the summer. Now, the Arctic sea ice, of course, freezes over in the winter and then melts back in the summertime, so it's in September where you see the minimum ice cover for the year. And this time series that you see here, starting in 1978 and going all the way up through 2005, shows that at the end of each summer, it's progressively less and less area covered by ice. So more and more open water being created at the end of the summer over time. And 2005 was the record year. It was the record year until 2007, and then look what happened. It dropped way down there. This is one of the biggest and most surprising changes we saw in the Arctic Ocean. It was about 20% below what it was during the previous minimum in 2005. And this is a comparison between the two end-of-summer ice maps for 2007, last year, versus 2005. And you can see how much more open water there is in the Arctic Ocean. Now I'm going to stop here and play a quick video for you. Now, before I start this, let me explain a little bit about what this is. You're looking at the North Pole. The North Pole's right here. This is a black and white movie that you're going to see. you can make out the shape of Greenland right here. This black space here is open water, open ocean. Here you can see the Scandinavian Peninsula. This is Siberia over here. This is northern Canada. There's Alaska. This is the Bering Sea right there. All this white stuff is sea ice. You also see some sort of filmy, cottony looking stuff in the image there. Those are clouds. And when I play this movie, you're going to see those clouds moving really fast. But I want you to pay attention to what's happening with the ice. So it should be starting. Here we go. Okay, so it starts in January and it's going to go all the way through September of last year. So we're into February now, and you see the ice starting to break apart around Bering Sea and the Chukchi Sea region off the coast of Alaska. Now you're starting to see it separate away from the coast of Siberia. Here it is in April. I'll stop it right here. This is about where it was 1 year ago today. Okay, this is the end of May last year, and you can see there's already open water along the north slope of Alaska and some open leads off of Siberia. We'll start it up again and see what happens during the summer. Now watch this region up here. As we get into July and August, you'll see what happens. It starts to really disappear. So this is where it ended up in September of last year. This is the minimum ice extent we have ever seen in all of our history of science, probably all in the history of the human race that we've ever witnessed in Antarctica. So there's definitely some very important climate change going on in the system that these satellite measurements are really helping us a lot to understand. Let me move on to the next slide here. Now I'm going to finish off talking a little bit about that ocean salinity that John mentioned when he gave me my introduction. Why do we want to measure ocean salinity from space? We all know that the sea is salty, but it turns out that ocean salinity is an important factor in ocean circulation. And what controls ocean salinity are changes in the global water cycle. When you have more rainfall in some part of the ocean, it's going to dilute the seawater, and that will change the ocean salinity. And if it evaporates more over in this other area that might be more prone to droughts, then you're going to have higher salinity because most of the fresh water is being taken off from the sea surface. Also, the melting and freezing of ice changes the salinity at the surface, as you might guess. So these changes in the water cycle affect the salinity, and the salinity affects the density, and the density affects the ocean circulation. And the ocean circulation, it turns out, affects how the ocean carries heat around, and that feeds back into the atmosphere. So that changes the rainfall patterns, and that feeds back into the salinity, which then, as you get the picture, it's kind of a coupled system, all right? And we really don't understand all of these feedback mechanisms very well because we've been missing all of this time a really good comprehensive way of observing the changes in ocean salinity all around the world, all at the same time. When we do it in ships, we're either over here or over there or over there, and so we can't really get a comprehensive synoptic view of ocean salinity. So that's what the Aquarius project is really all about, and I'm going to end the talk there with this picture of the Aquarius satellite. I will make one correction to what John said. We're not launching it in 2009. I'm sorry to say there's been a slight delay. It's launching in 2010. But it will be 2 years from now, May 2010, we're launching this mission to explore the Earth in a new way, which is measuring ocean salinity. So I thank you very much for your attention. I hope you enjoyed the show. Okay, thank you very much.
Thanks, Gary, for that. Great job. That was wonderful. I just thanked Gary for that great job. Thank you, Dr. Lagerloef. That was fascinating information. Just tip of the iceberg. All right, we're certainly better for it anyhow. So with that, I just want you to remember to take a look at the fantastic service display boards we have. They're probably out there by the badge bars. So we're adjourned.
Seattle Rotary Online is made possible in part by a grant from First Choice Health, working with the Washington Health Information Collaborative to use technology to bring better health care to patients throughout the Pacific Northwest. First Choice Health.